Okay, this is going to be the first video. We're going to talk about visualizing surfaces in 3D space. So these are given by equations relating x, y, and z. And the way to do this in general is to take this 3D problem and try and chop it up into a series of 2D problems. So literally, we're going to chop it. We're going to take this meat cleaver here, and instead of looking at this crazy surface, this mystery surface, we don't know what it is, we're just going to imagine chopping it with this huge cleaver. In fact, should really be a much bigger cleaver than I've drawn it. And just imagine slicing it in some direction that's, say, parallel to the XZ plane. I mean, if you imagine that this knife, this big blade, is like a plane, it's like the XZ plane, then if we slice this surface, we're going to get this green goo. This is like the blood that stays on the cleaver. Right, so after the slice, maybe this mark is left on the cleaver. You want to think of this cleaver as sort of being the XZ plane. All right, so that's just, of course, get rid of that ugly looking picture there. But the whole idea is to take these kinds of slices, or we could have moved it over. We could have looked at this slice that's slightly further along, or this slice that's more on the negative Y region. All of these slices being parallel to the XZ plane. Well, if you actually look at what we're really doing, you can think of these cleavers as being large planes. So these planes are actually given by these equations here. Y equal to 0, y equal to -1, y equal to 1, and in general, y equal to some constant. These planes here are all parallel to this XZ plane. In fact, this actually is the XZ axis, or the XZ plane, right there. Y equal to 0. So you're just kind of imagining that plane right there and how it intersects the surface, what kind of mark the surface leaves on it after we slice it. Or, of course, I mean, there's nothing special about picking y equal to constant. If you pick z equal to constant, then these would be kind of horizontal slices. You can imagine the blade is now parallel to the xy plane, and you're slicing it up and down. So those would be pictures right here. There's z equals 0 plane. Of course, z equals 0 also happens to be the xy plane. And then all of the other z equal constant spaces are parallel to it. So we're just looking at what would happen if we took some weird surface and we intersected it with one of these planes. It would leave a curve on that plane. And hopefully, if we can understand what each of these 2D slices look like, each of these curves look like, then we can put them back together and get a better understanding of what the surface itself looks like. And since I've mentioned these two so far, I may as well mention the last one. We could take x equal constant, the x-axis here is kind of jettisoning out of the page, and the planes there would kind of look like, I have it right there, they're kind of stacked out like that. So this x equals 0 in the middle there, that would be our, of course, yz plane. And we're just imagining some surface sitting inside there getting cut up by these planes and the kind of marks that are left on it, the kind of curves that are left on it. So, how do we actually go about doing this? How do you find the intersection between these planes, which are literally given by these equations? I mean, this plane is y equal -1. It's the set of all points of the form something, comma, -1, comma, something. That's what this plane actually is. So y equals -1 literally represents something parallel to the xz plane, but with y coordinate fixed at -1. Okay, so how do we find the intersection of that and some mystery surface given by some mystery equation involving x, y, and z? Well, actually, I suppose we'd know what the equation is. But let's revisit a simple two-dimensional problem and see what it looks like. If we just had two variables here, this was basic algebra. If you had this parabola, for instance, y equal to x squared, and this line y equal to -1/2 x plus 1, how would you find the places they intersect? I mean, we're trying to intersect all of these planes that we're thinking of as meat cleavers with this kind of mystery surface given by an equation that I haven't really written yet. Well, how do you find the geometric intersection of two things? Well, you solve these equations simultaneously. You're looking for x comma y values that lie on both of these shapes, which is to say that they satisfy both of these equations. So you solve them at the same time. And if y is equal to x squared and it's equal to negative 1/2 x plus 1, well, you can just equate them. X plus 1. You kind of plug one equation in for y in the other equation. And then you can solve the x's, and then you can go back and solve the y's by plugging back in. So in other words, to find geometric intersections of graphs, you just simultaneously solve the equations. So if we had some surface, some mystery surface, and I don't know, I want to intersect it with maybe y equals, say, -3. -3 would be somewhere out here in green. Not a very good drawing because I'm doing it by hand. But let's say there's my y equal to -3, or I have one out here, maybe 3. There's my y equal 3 surface. And I have some kind of mystery surface floating around out here, whatever it may look like. Then all I have to do, if this equation is given by something involving x, y, and z, like x squared plus y squared minus z squared equals 5 or something like that. By the way, this equation certainly does not describe a weird looking shape like that. We will see in another video what this type of equation does actually look like. But just because I have no idea what kind of equation would give that, let's just say it's given by this equation. And I want to cut it by the plane y equals to 3, which again is parallel to the xz axis. What would it look like? What would that slice look like? Okay, how do we figure that out? Well, you would just simultaneously solve these two equations, same as we did in the 2D case over here. You just simultaneously solve these equations, y equals 3 and x squared plus y squared minus z squared equals 5. Well, plugging 3 in where I see y, you would just get x squared plus 3 squared minus z squared equals 5. This is an equation that only relates x and z, which makes good sense because this should be an equation on this plane. This isn't exactly the xz plane. The xz plane would have been y equals 0, but it's parallel to the xz plane, so it makes good sense to think of it as sort of like a translated xz plane, or an xz plane that's been shifted over. In any case, when you graph what this looks like in the xz plane, it's going to exactly give you the cut. It's going to give you that slice, that shape that you get when you slice the surface with the plane y equals 3. So it's a general rule it's worth recording right here. Looking at the intersection of a surface with the y equals 3 plane, that kind of butcher knife, slicing the surface by that plane, parallel to the xz plane, is the same as plugging in 3 in place of y in the equation for it, for that surface, like we did over here. We just plugged in 3 instead of y. Okay, so the resulting equation, which is only going to involve x and z, because we plugged in something for y, can then be graphed on the xz coordinate plane. And like I said, it's exactly that kind of slice, the kind of bloody remain left on the butcher knife, the cleaver. Okay, so maybe some examples will help us to better understand this. But before I do, I'll just quickly mention, I said it for y, but it works for x and it works for z. Here you would plug in y equals any one of these values depending on which y plane you want to slice it by. But if you want to slice it by these horizontal z planes, you just plug in z equal 1 into the equation. And then you'd get something involving x and y, and that would describe some kind of curve. Or you'd fix x equal -1 here if you wanted to look at it sliced with that last plane. So it's just whatever plane you're slicing by, you replace the variable. Again, you're just solving these equations simultaneously. So now let's look at a couple of examples to finish the video off. So you all know that the sphere is given by the equation x squared plus y squared plus z squared equals 1. Well, if for no other reason than, if I put the square root here, then that's the distance of a point x, y, z to the origin. So we're saying the distance is equal to 1, or 1, yeah. So the distance is equal to 1, the set of all things unit distance from the origin is obviously going to make a sphere. All right, so what can we do here? We can take this example, and we can imagine slicing it. So I just drag it over here so that we can run it through these meat cleavers and see what it all looks like. Now this sphere is actually a little too big for this picture. Maybe it looks something like something like that. And you can see that depending on where you're intersecting it, it might intersect in a point with z equal 1. It might intersect in a circle on that plane or another point down here. So we're looking at slices of this sphere. So let's go open up Microsoft Mathematics here, and let's take a look at a couple of pictures here. First of all, I drew the parallel planes separately. You might be wondering, what do they look like all at once? So let's just quickly take a look at what that should look like. All right. Okay, so here I've drawn the x constant planes and z constant. X equal to 1 and negative 1, and z equal to 1 and negative 1, just to kind of show you that these directions you're slicing them in are perpendicular to one another, depending on whether it's x or z. And you can imagine the y would also be perpendicular to both. It would kind of jump out at the screen at you, kind of cap off that cube sitting inside of there. Okay, now since we were talking about the sphere, let's open that up in Microsoft Mathematics. I already have it written or done, so here we go. There's the sphere, and these are the z constant planes. What you'll notice is that this plane right here, this top plane, that's my z equal 1 plane. And it touches the sphere at exactly 1 point, just the very top, the very north pole. On the other hand, this z equals 0 plane down here intersects it in a circle. It's where this mouse cursor is. And then we have the south pole, again, intersecting at a point. That's my z equal to negative 1 plane down there. And then you have this z equal 2 plane, which is just out there in the middle of nowhere. And it's not touching the sphere at all. Now let's see what that all comes out to in terms of equations. Again, figuring out what the intersection should look like in the xy plane, or in these shifts of the xy plane, should come from just plugging in these different values of z into the original equation. So let's go to the original equation of the sphere, and let's just plug in different values for z and see what happens. When I plug in z equal to 2, which was that plane over here that never touched anything up there, well, think about it. You plug in z equal 2 into there, x squared plus y squared plus 4 equals 1. Because 2 squared is 4, right? But then that implies x squared plus y squared equals negative 3. But x squared and y squared are squares. They got to be positive. There's no way on earth they could equal negative 3. So there is no simultaneous solution of z equal to 2 and x squared plus y squared plus z squared equal to 1. So that plane and the sphere simply do not intersect. That's the geometric interpretation of the algebra we just did. What if, on the other hand, I plugged in z equal to 1? Well, z squared would also be 1. So x squared plus y squared plus 1 equals 1. Subtracting 1 from both sides, x squared plus y squared would have to equal 0. But again, the only things, if regardless of whether x or y are negative, squaring gets rid of the negative sign. This is either positive or 0, and the only way it could possibly be 0 is if both x and y were simultaneously 0. In other words, the only point x comma y that obeys x squared plus y squared equals 0 is the origin, x equals 0, y equals 0, which is just a point. Well, that makes sense, because the z equal 1 plane is up here, and it touches the sphere exactly at that 1 point up there, the very top, the very north pole. Something similar happens at the south pole, z equal to negative 1, and it's easy to see why when you look at the equations. If we plugged in z equal to negative 1 instead of 1, again, squaring it gets rid of the negative sign. You'd still be looking at x squared plus y squared plus 1 equals 1. Because the negative gets canceled out by your squaring, which leads us to exactly the same problem. And we only have x squared plus y squared equals 0, so we're only looking at the origin. That's why it only intersects at 1 point. So finally, if we look at z equals 0, then plugging in 0 there would just give us x squared plus y squared equals 1, which is the unit circle in the xy plane. And doesn't that exactly look like the intersection there, here? It's exactly the unit circle. The full radius of the sphere is being realized. But let's jazz this up a little. Instead of this boring, let's find it. There we go. Z equal 2 plane. That's not helping anybody. That's not an interesting plane. How about z equal to 1/2? Z equal to 0.5. enter graph, and there we go. So now that's this plane right here. This kind of one in the middle of the z equal 1 and z equals 0 graphs. You'll notice that it intersects the sphere in a circle, but it's a circle of smaller radius than the main equatorial circle. The equatorial circle has radius 1. This has radius less than 1. Let's actually figure it out real quick. So if we made z equal to 1/2 now, again, you just plug that into the formula. X squared plus y squared plus, I guess a half squared is a fourth, equals 1. Subtracting a fourth from both sides, x squared plus y squared equals 3/4. And if you take the square root of this, I mean, remember, this is the radius of the circle squared. So radical 3 over 2 is the radius of that smaller circle. So now if you actually imagine what this looks like. So I think I still have my sphere here being cut up by these z-axes. There's a circle here that's being cut out on the equator. If I looked at, let's suppose this isn't z equal 1, and this isn't z equal 1. If I took this plane and I made it a little bit closer, then that cut would be another circle, but it would be a slightly smaller radius than the equatorial circle. And the higher up cuts become smaller and smaller and smaller until they kind of converge to this point. So if you're looking at the picture is rather pretty. The z equals 0 cut is what I have here as this big blue circle of radius 1. This is what it looks like. So what I'm imagining doing is looking at all of these individual cuts floating in space and then smashing them down onto the same plane so that we can compare the sizes of those different circles. And here it is. As z increases, those circles shrink in, and then when you reach z equal to 1, that's the North Pole right there. It reaches this point. So it's just a nice picture of how you can kind of visualize the sphere by looking at these z cuts. Now, because of the symmetry of the sphere, you can imagine looking at the x cuts or the y cuts is going to give you a similar picture either way. So we'll look at other examples in the next several videos, hopefully more interesting. But the idea is you're supposed to look at these kind of 2D slices, the 1D curves on these 2D planes, and kind of patch them together to get a feeling for what the shape looks like.